Einstein's Theory of Relativity, Proved and Simplified, by Zachariah Araya. On February 18th, 2021, the most complex rover ever created, Perseverance, landed on Mars. It was the size of a car and weighed 1 metric ton. But without Einstein's contribution, his theory of relativity, this rover wouldn't have landed. Nor would Neil Armstrong have stepped foot on the moon, or Mae Jemison realize her dream of becoming the first African American woman to become an astronaut and go to space. To put it simply, the theory of relativity is a theory explaining how space and time interact and whether or not they are relative. The purpose of my project is to inform and demonstrate the way Einstein's theory of general and special relativity are relevant to our everyday lives. For example, how does this theory help us understand our place in the universe? How does this theory help us understand how gravity manipulates matter? And how does it contribute to space exploration? My experiment will test how time and space interact in different inertial frames of reference. Without Albert Einstein, we would still believe Isaac Newton's theory. English mathematician, physicist, astronomer, theologian, and author Sir Isaac Newton is most famous for his three laws of motion. But did you know that he discovered his own theory of relativity centuries before Einstein was alive? Newton's theory was that the laws of physics are the same for all observers in any inertial state of reference within the relativity to one another. This was the principle of relativity. The speed of light in a vacuum is the same for all observers, unaffected by any alternative or relative motion or the movement of the light source. A vacuum is a void without matter, and space is almost an absolute vacuum, but is not a vacuum because of one thing, gravity, which is caused by mass and matter. Translation: if we had a void, Newton's three laws of motion would apply to all observers, whether they were moving or not. Therefore, the speed of light wouldn't change for any observers, regardless of the observer moving or the light source moving. To simplify further, what Isaac Newton is saying is that I will see the light of a lamp as it's being turned on at the same time a friend does, regardless of how close or far we actually are, or if we are moving or not. That's because at the time, the speed of light was thought of as infinite, or too fast to measure. By the time Einstein was born, the speed of light had already been discovered by an astronomer. Newton's theory is what Einstein disproved with his theory of general and special relativity. His famous equation, E equals mc squared, proves him right. With simple math, Einstein was able to figure out that energy, E, and mass, m, are inversely proportional, or interchangeable, as is shown by the equal sign. C squared is the constant, meaning speed of light squared. This means that light is affected by gravity because light has energy, and since it has energy, it also has mass because we just learned that mass and energy are interchangeable. My experiment. A runner will be running at 14 miles per hour or 22 kilometers an hour, the average speed of a 12-year-old, and then at walking speed and carrying a ball. The ball will then be dropped, and the drop will be observed from two different perspectives. One perspective from the runner, and the other from a bystander who's not moving relative to the runner. My hypothesis is that the runner will see the ball drop on a straight line, versus the bystander who will see the ball drop differently. My reasoning is that the runner, who will be running at 22 kilometers an hour, is also bringing the ball along with them. Therefore, the ball is also moving at 22 kilometers an hour. And since they are both moving at the same pace relative to each other, it's as if the ball and runner are moving at 0 kilometers an hour to each other. But, on the other hand, the bystander isn't moving. Therefore, the ball is moving much quicker than the bystander. Even after the runner lets go, the ball will still keep its forward momentum until drag and gravity make it stop. That is why I think the bystander will see the ball drop differently. The first one is my control. I'm just standing still and dropping the ball. Here's from the runner's perspective. Now here's from the bystander's perspective. Now, here at walking speed is part 2. This is the while running perspective, the runner's perspective. Now, I'm walking, but this is a slow motion video to show how it affects each speed affects how the ball drops. And here's the bystander at rest perspective. You can see how it's slightly curving towards the right because the ball's momentum is keeping it moving forward. Here's while running. It still looks like it's moving straight down. And here's the bystanders at rest perspective. The results speak for themselves. The runner who is running with the ball sees the ball drop straight down, while the bystander sees the ball drop on a parabolic curve because they are at rest compared to the motion of the runner and the ball. The different inertial frames of reference, inertia being a property of matter, where an object continues in its resting state or uniform motion until acted upon by another force, showed two very different results, proving Einstein right and disproving Newton's theory of relativity. Well, now, this was a fun experiment, but how does Einstein's theory apply in the real world? How did it get us to space? Well, let's talk about Einstein and his theory. Remember how I told you how without Einstein's contribution, we would have never landed on the moon or gone to space at all. That's because when he figured out light is affected by gravity, we were able to calculate the path light will take. No, the rover and the space shuttles that take the astronauts to space are not made of light, but the farther the rover gets away from us, the longer the light has to travel to reflect off the rover and back to Earth, and that changes where we see the rover in orbit. This means that we see the moon where it was 30 seconds before, because light takes 30 seconds to bounce off the moon and reach Earth. The same thing happens with Mars, but with a longer time period of about 7 minutes and 24 seconds at some points in its orbit around the Sun, because its orbit around the Sun is not perfectly circular. Conclusion? I conclude that Einstein's theory of relativity does indeed disprove Newton's theory of relativity, and that without this important revelation, space travel would have been unattainable. Here's my bibliography and my websites that I used.